Hello, in this video we'll be going over resistance in circuits using Play-Doh. For our experiment, we wanted to see if we could accurately predict the resistance of Play-Doh. We created a cylindrical Play-Doh resistor and measured resistivity at different lengths using the equation R equals L over A. Then we tested whether those resistors would behave as expected in a real circuit with an LED and a motor. Our main research question was, can we use the measured resistivity of Play-Doh to design a custom resistor that functions predictably within a circuit containing an LED and a motor? What we found was that the resistance increased as the length increased, which matches the equation we used. This showed that our model was pretty accurate. We also found that the LED needed a certain voltage drop to light up, which we were able to reach using our setup. In terms of context, Play-Doh has a high resistivity because of its salt and water content, and LEDs only allow current to flow in one direction. So resistors are important to prevent too much current and protect the circuit. Before starting, we predicted that resistance would increase as length increased, and our measured and calculated values would be close. Our results were not as predicted, but not too far off. We also expected that Play-Doh would dry out over time, increasing resistance since losing moisture reduces the number of ions that can carry a charge. Finally, these diagrams show how our circuit was set up and how energy moves through the system. The battery provides energy which flows through resistor, LED, and motor. We can see that electricity is the main connector of each of these components in the circuit. This helps us visualize how our Play-Doh resistor fits into a real circuit and confirms that it behaved in a predictable and functional way.
Now we'll go over our data. We used 3 batteries for our circuit with a voltage drop of 4.56. We had an LED in series and then a resistor, motor, and capacitor all in parallel. And then we have our values that we measured in this table. And then our Play-Doh duct data, we built a Play-Doh duct which we use as a resistor. It was shaped like a cone, so we used the formula half times length times base times height for our area, which gave us 0.0026 meters squared. And then we calculated our resistance, giving us a predicted resistance. We also calculated a predicted voltage and current. So for our resistance, we used our resistivity from our pre-lab with the simple cylindrical resistor, which was 0.55 ohms divided by meters. And then that gave us a resistance of 13.75 ohms. But our actual resistance when we divided our voltage by current gave us 33.94 ohms, which is pretty far off that mark. So we'll talk about later why that might have happened. Our predicted voltage was 1.49 volts. Our actual was 1.11, so that was pretty close. And then our current was also pretty far off. We got 0.1 for our predicted, and then our actual was 0.0327 amps. So we did our uncertainty for our Play-Doh resistivity. Using Linus, we got 0.00144. And then propagating that using our formula for resistance gave us a standard error for our resistance of 0.036 ohms. And as talked about earlier, this is not enough to account for our results because they're pretty far off. But we can talk about later how the Play-Doh and our batteries being drained might have led to that.
Data is supported by the model R equals PL over A because resistance increased as the length of our Play-Doh increased. The LED also behaved as expected. We did not have much trouble with our model. However, our predicted resistance value was 13.75 ohms and our measured value was 33.94. This shows that although the model predicted the overall trend correctly, it did not match the real behavior of the circuit. This suggests that the model was oversimplified by the system by assuming the Play-Doh had a perfectly uniform shape and constant resistivity. This could be caused by the fact that Play-Doh can dry out over the time and moisture is lost and the number of mobile ionic charges decreases. This would increase the resistance and help explain why the actual resistance may have been higher than the predicted. And then for our sources of error, the Play-Doh could have changed shape or thickness during the experiment. The Play-Doh could have dried out over time, reducing moisture. The LED wires might not have been fully pressed into the Play-Doh, causing weak electrical contact, and then the battery voltage may have dropped as it was used, changing the amount of power delivered to the circuit. Then for our reflection, our resistance was higher than it predicted. For the overall circuit, this showed that our model captured the general trend by the real Play-Doh resistor behaved less ideally than expected. In the future, we would improve the experiment by making the Play-Doh more uniform in shape, measuring its dimensions more carefully, testing it faster before it dries out, and making sure all the wires and LED leads have more consistent contact. We could also repeat the experiment in more trials to improve reliability and compare results across multiple resistor shapes to make sure.